Let's look at example number 4. Now we have a word problem that we're going to be dealing with. First of all, they tell us the greatest common factor has many uses. Among them, the greatest common factor lets us find out the maximum size of squares that cover a rectangle. When we solve problems like this, we cannot have any gaps or any overlapping squares. Of course, the maximum size squares will help us find the minimum number of squares needed. We've already covered this when we talked about example 1. We found the greatest common factor of the dimensions as the largest square that we could put in there that covered the area without overlapping or having any gaps. So let's apply that again here for this problem. This is a rectangular computer table, measures 30 inches by 50 inches. We need to cover it with square tiles. What is the side length of the largest square tile we can use to completely cover the table without overlap or gaps? So we have a table here, a rectangular table, measures 30 inches this way by 50 inches this way. We first need to figure out what's the largest square that we can put in there, the largest amount of squares. So we want or largest size of squares, or largest size of squares. So we need to find the greatest common factor of 30 and 50. And I'm going to use the Euclid's algorithm to do this. So I'm going to divide 50 divided by 30 and get 1 time, remainder of 20. I'm going to continue until I get a remainder of 0. Now I have a remainder of 0. The last divisor, of course, is my greatest common factor. Now what that tells me is the largest square that we can use measures 10 inches by 10 inches. Remember, it's a square, so all 4 sides have to be the same. So 10 inches by 10 inches is the largest square that we can use. Now the next part wants to know how many of those squares that are 10 by 10 do we need. Well, let's first look at this dimension that measures 30 inches. If we're going to fill that in with squares that measure 10 inches by 10 inches, we could fit 3 of those in along that way. We would have 10 inches here, 10 inches here, 10 inches there. If we look at the other dimension, 50 inches can be split into 5 equal pieces. Now I know they don't look like squares here. But you got to remember they are squares, so we'd have 10, 10, 10, 10, and 10. That means we had 3 squares one way by 5 squares another way. If we multiply them, we get 15 squares. Count those squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We would use 15 squares that measure 10 inches by 10 inches. Now, if this were a giant chunk of cheese in a factory, would it change the thinking or the calculations we just did? Of course not. Of course not. If we're taking a large rectangular piece of cheese and cutting it into squares, the largest square we could have would be 10 inches by 10 inches. And if the chunk of cheese measured 30 inches by 50 inches, again, the most squares that we could have would be 15 squares. So it doesn't matter what we're talking about. If we've got a rectangle and we want to put it into square, fill it with squares, we find the greatest common factor to find the size of the square, the largest size of the square that we could use, and then we calculate how many of those squares we can fit in that area.